Okay, let's take a look at another example. This is number 6. And what we want to do is we want to try to integrate this integrand. Now the problem with this is if you just had sine, that's not a problem. If you just had the x minus 1, that would not be a problem. But now how do you integrate like x times the sine of x? So remember, and I'm sorry to repeat this over and over, integration by parts says, is there a way to shift the derivative off the v term onto the u term? So we're going to try something. And remember, whatever you choose for your dv, you better be able to integrate it. Otherwise, you're just making the problem harder. Now, there are some exceptions to that, which I'll talk about. So what I'm going to do is I'm going to try to let the u be the sine and the dv be the x minus 1. Okay? So we need to figure out what dv is. So I differentiate the sine, which is the cosine. Then we have to use the chain rule, right? That's where the pi comes from. And we quote multiply both sides by the dx. So my du is going to be this. And if this is my dv, then by the chain rule, this is a u to a power 1. So then this becomes 1/2 u to the power 2. Forget the constant of integration. And so now what we've got is the following. So we started out with this. Here's our u, here's our dv, minus our v and my du. Now what I do is I ask myself the question, are we better off than when we started? So if I take a look at what we started with was x sine. Now we're left with, just look at the integral, the new integral, the v du. This is even worse. And in fact, I want you to notice something very interesting here. You took an x minus a 1 and you turned it into a 1/2 x minus a 1 squared. That definitely tells you that that was the wrong choice. So we'll try something else. So let's try the following. Let's let the u be this guy. Whatever's left over has to be the dv. So we're going to take, and we have to integrate this. Now what's going to happen is you're going to be, obviously your quote u is going to be the pi x. So you're going to need a pi, and you're going to have to take out a pi. So the integral of the sine of u is going to be minus the cosine. Then we have this extra factor of the 1 over pi. Again, that becomes, you have to have a pi here, and you have to take one out. And so when I differentiate the u, I just get 1, quote, multiplied by dx. And now we look at what we've got. So integration by parts says u dv equals u v minus the integral of your v du, and then so I could pull out the minus, becomes plus 1 over pi, and then you could integrate cosine. So you're going to get the integral of this guy, so the negatives are going to cancel. So we can expand out. So I take x times this guy, and then negative 1 times negative. So we're going to get a negative x cosine. We're going to get plus, the negatives are going to cancel. And then the minus becomes a plus. And now we can integrate the cosine easily. That's what we're going to do next. Sorry, because of humidity, papers are sticky, so... Okay, so we now integrate the cosine. Now notice this is much easier to integrate, right, than what we started. So the integral of the cosine is going to be the sine, but you're going to need another, what, pi to go with your dx. Then we take out the pi. And then so we now have the constant of integration. And now you just put everything together. And so we Notice what happened is when you chose the other one, you got rid of the x's terms. So that's the clue, is that you're trying to shift the derivative so that you get rid of the unwanted terms. And here is your final answer. And how would you check to see if this is correct? Well, what you do is obviously differentiate. And you can use, if you go on the internet and use something called Wolfram Alpha, you can actually verify. You could type in the commands, and you're more than welcome to use that. We did have Mathematica and MATLAB available, but because of the budget cuts, we have not been able to come up with the money for using Mathematica. Otherwise, I would use it in class. Let's take a look at another example here. Number 8. Notice what I'm doing is I'm doing all the even problems, and the reason for that is because I'm going to assign you the odd problems, and you can check the answers in the back of the book. Also, just as a goofy remark, this way you can't tell if I'm doing them right, because I'm doing the even. No, hopefully I can do this. Now, what's wrong with this? If you compare this with the previous problem, you had x's and signs. Now you have something squared in this. So you're going to probably have to do some finagling twice. So keep this in mind. The previous problem we had just x to the power 1 and cosine sines, whatever. Now we have a squared term, so we may have to, we let u be this guy, excuse me, this guy. We're going to try maybe the same thing. So let's see what happens. So remember, what we're starting out with is a t squared. So if I let u be t squared, whatever's left over has to be my dv. And we know how to integrate signs. So we're going to be shifting the derivative off the v onto the u term, which is going to drop down the power of this. So we let u be t squared. Whatever is left over now becomes our dv. Can we integrate the sign? Yes, we know how to do that. So we're going to differentiate this guy. It's going to become 2t. Excuse me, this is not supposed to be there. And then we multiply both sides. And we get du. I can integrate the sign to get a negative cosine. Remember, your b is going to have to be the beta t. So you're going to have to put a beta in and take one out. So now what we do is we substitute in our u dv equals u, which is this guy, v, which is this guy, minus the integral of v, and my du is 2t dt. So now we can pull out the 2's and rearrange a little bit. So we just do a little bit of algebra to simplify things. And so now we ask ourselves the question, notice that what happened is we went from a t squared now to a t, which is good. So we're going to probably have to do this again. So let's just take this part out and do it again. So what we're going to be doing is shifting a derivative. So we're going to try to be differentiating t. And we have to integrate this guy. So if we let u be t, what's left over is our dv. Can I differentiate this? Yeah, it's 1, so I just cross-multiply by quote dt. Can I integrate the cosine? Yes, you're going to get the sign, but remember you need that extra beta there, dt. Okay, so, excuse me, there's a dt here. And we do integration by parts. So my u dv becomes u, this guy, uv minus the integral of v, and my du is just a dt. Notice we've got a sine. We know how to integrate that. Now you're going to have to pull out the beta term, and we have to integrate this guy. You're going to need another beta, so you're going to pull another one out. The sine becomes a negative cosine. Now you can throw in your constant of integration, and you can put all this together. So what we do is we've got the t squared. So we had the t. This was our uv from the first thing. Then we had this guy. We just did that, and now we put everything in, and we get this lovely object. And again, you can go to Wolfram Alpha and check, or you could differentiate this and compare it with what you had to start with. And notice that differentiating stuff here could be quite messy, and oftentimes you're going to make a mistake in trying to check it. The fastest thing is just to use Wolfram Alpha. So we have a problem. How do I integrate? It's a very similar problem, except we have hyperbolic trig functions. So it's the same type of thing. We're going to have to be shifting a derivative onto this guy to try to bring it down. And remember, whatever you choose for your dv, you better be able to integrate it, or there's something else that could possibly happen. So when I have, say, ddt subscript 1, it doesn't mean the insecticide. It means don't do this, okay? So if you let excuse me, if you make the wrong substitution, so if you let the hyperbolic cosh be your u and whatever's left over, so in other words, if I let this be my u, then this would be, what's left over is my dv. The problem with this is when I go to integrate, I'm going to get what? I've changed an x into an x squared. That's worse. I've made the problem harder. So ddt subscript 2 means do this. So here's what we do. We want to shift the derivative off onto here to get rid of the, it seems to be, there, that's a little clearer. So we're going to shift the derivative off of this onto the x. And now if you go to formula, I think this is 104 in your reference in the back of your book, you can find out what it turns out the integral of the hyperbolic cosine is the hyperbolic sine, not the negative. Okay. You remember the hyperbolic trig functions are not periodic, and they arise. Where's the typical example? Oh yeah, if you take and you look outside, and you have the electric poles, and if you look at the wire and how it sags, and you think it's maybe a parabola, it turns out that that's not true. It's actually a hyperbolic function. So anyway, going back to this, so we're trying to shift the derivative off of this guy onto the x. So what we're going to do is let our u be this, whatever's left over is my dv. Excuse me, so du by dx is just 1, so du is just dx. And so if whatever's left over, we're going to have to be able to integrate it, right? So here, my new u is going to be this ax, so you differentiate that, you get a. So your du is going to need an a, so you're going to have to put in an a and take one out. Okay, so that's what we've done here. So now you've got your hyperbolic cosh of a u du. And if you just go to your reference, that turns out to be the hyperbolic sine, not the minus, and then plus an arbitrary constant. So So now we ask ourselves the question, are we in a better shape than what we started with? Okay, so this was my u, this is my dv. So we're going to have u and then v minus the integral of v, which is this guy, and du is dx. So you could pull out the 1 over a, and you could just look up now what the integral of a hyperbolic sine is. And that's going to be your hyperbolic cosine. So you could just look that up in your reference, and you'll have access to this. That's when you're doing your quizzes and your tests, so you should be able to, you're welcome to use the formula sheet. And so if we put everything together, we end up with this lovely solution down here. So if you, when you're doing this, if you want to check yourself, you also look at the back of the book, right, for the odd questions. Or you can go to online to something called Wolfram Alpha and actually check your answers. Let's take another example, number 18. Okay, now, this one's going to be a little bit different than what the previous ones were. So what we've got here is the following. We have a problem. We have a combination of exponential and trig functions. Now, I know how to integrate or differentiate an exponential. I know how to differentiate or integrate a trig function. So I'm just going to try something. Suppose I let u be my e to the minus theta. Whatever is left over has to be my du. I mean my dv, excuse me. Okay, so if we do that, we differentiate du. So that becomes minus e to the minus theta, then quote cross multiply. We'll let my dv be this stuff, whatever's left over. I know how to integrate the cosine, so this is going to be another u problem, right? So this is going to be your new u, so you're going to have to put in a 2, take out a 2. The integral of the cosine gives me sine. So now, so I'm going to move stuff here. So now we put in our u, our v, minus, and then we have our v and du. So we could take the negatives, cancel, I could take the 1/2 out. And now we have to integrate. Now, there's a problem here. What we started with was the e to the minus, so we have our u and v minus, and then remember the negatives cancel one. And now we're back to, this stage. Now, wait a minute. Have we made any progress? In other words, what we're saying is you've transformed this integral into this integral. Now that doesn't look like any progress. You've just changed the cosine to a sine. Could that help us? The answer is yes. So what's happened is integration by parts has changed the cosine into a sine. Forget about the pluses and minuses. If we do this again, what's going to happen? The sine is going to change back into cosine. Now that looks like we've accomplished absolutely nothing. Wrong. What's going to happen is when we change the sine back into cosine, we're going to have the unknown integral on this side and on this side, and we can put them together. So we're going to do it again. So I do the same thing. Now you have to be careful. You've got to let your u be the same thing and your dv be what's left over. So just let u be this, differentiate. You let dv be this, integrate. And we get the following. So I now have this thing, no. We go uv, so we do the same thing. This is my u, this is my dv. So it becomes uv minus the v du. Negatives, negatives, negatives gives me a negative. Pull out the 1/2. So just this new integral, not the original one, but just part of it, is this guy. But this is what we started with. But that's okay. Let's put all this together now. So what we've got is the original. We integrated by parts once. We introduced the sign back again. Then we did another integration by parts on this guy. And so here's how I want you to think of this. This is the original problem. Think of it as like a big X. Okay? And notice what happens is, so you integrated by parts once, you got this, and then you had to integrate by parts again, so you got an additional term, and your unknown shows up again. So it shows up on this side, and it shows up as a minus 1/2 of what you started with. So you're thinking of this as a big X, and this is a minus 1/2 of X. And what you're going to do now is you're going to put these two guys together and solve for it. So if I let this be my unknown, notice that there's a 1/2 here, so I have to distribute, so you get it minus 1/4, and you're going to get minus 1/4. And so you get, notice that you get the X, oops, here, and you get a 1/2, 1/2, a minus 1/4 X on this side. That's very nice. Now you can what? Solve, put these guys together, so you're going to add a 1/4 X to this side, and here's your what's left over. And so it's just a little bit of algebra. Boy, this humidity is really, papers are really sticking. And so you put all this stuff together, and you end up with this. Notice the problem, that when I did an integration by parts once, I shifted the derivative off this onto this, derivative of this off to this. So then you got a sign, and then you have to do it again. You have to make the same manipulations. Now, suppose we try the other way. So in other words, what I'm going to do is let the cosine be my u, and the e to the minus theta d theta be my dv. And guess what's going to happen? It's the same thing. Okay, so you're going to have to, so I want you guys to do that.